Welcome back to Principles of Electronics, lesson number 6. Today we're going to be talking about diodes. Diode is a very important component we use in many different applications in electronics. In this lesson I'm going to go over just some basics. But let's answer the question, what is a diode? A diode, I have the picture here. This is a physical picture of a diode. This is the symbol of a diode. As you can see, the diode has an anode, which is a plus, or the positive side, and it has a cathode, which is the negative side. This correlates to this actual picture here. Now, if we were to remove this silicon cover, we would have a p-type material here and an n-type material here. I'm not going to get into the ins and outs of the p-type and n-type material, but this is what is inside this little silicon cylinder. The part itself has an indicator on it. That's usually a white stripe or a silver stripe. That white or silver stripe indicates the cathode side of the component, and that is very important. If you remember in LEDs, we talked about polarity, that the LED had to be in a certain way for current to flow. In that case, it had to flow to light a light. Here we're not lighting a light, but we are controlling the way current flows. Now, in conventional thinking, and I'll talk about this in just a minute, but in conventional theory, current flows from the positive to the negative. Now, let me jump over here real quick. Just give you a quick idea of the differences between this two. When we design, usually deal with current flow in the conventional manner. That means current travels from the positive to the negative in any circuit that we have. For instance, over here, from the positive to the negative. Well, what they found out years later was that electron flows actually from the negative to the positive. So the electrons are actually flowing this way. Now, what does this matter for us? Really nothing, because in today's day and terms, we pretty much use conventional thinking in all of our designs. So we're going to stick with that. So back to what is a diode. Our current then flows from positive to negative. What happens is, in a diode, when it is in series in a circuit, it does not allow current to travel that way. It blocks it. I like to see this little thing as a dam here, and it blocks the current. Again, we're talking about conventional thinking. Now, let me equate this with something like this. Let's say you had, we'll go back to our water example. Let's say we had this tube of water, and we put a directional valve in this tube. And let's say we had water flowing this way. This is our current. Our water's flowing, our current's flowing. It hits this gate goes up, water continues to flow. But if water tries to flow the opposite direction, this way, this little valve shuts and does not allow the water to go through. This is how a diode works. It allows current to flow one direction, but when current tries to flow the other direction, it stops it. All right, so that is what a diode is. Let's talk about a few other terms here. If I were to, I'm going to draw two different diodes, and then we're going to discuss biasing. So here's two diodes. Let's just pretend they're the same. And let's say I hook up a battery to where this is the plus and this is the minus. Now, if this is the plus and this is the minus, which this is the cathode, that's positive, or the anode side, then in electron flow theory, I'm going to get current that's really going to travel this way. Okay? Now again, I'm jumping between conventional and electron flow, but that's really how it works. Now this is called, even though we don't use that terminology, this is called forward bias. Now, if we reverse that battery and we put plus here and minus here, This then, in other words, in actual electron flow theory, this is called reverse bias. Now, what does that all mean? Well, this is important because if we were to chart this, I'm going to make a chart, and I'm going to say this is my voltage forward biased, this is my voltage reversed bias, and this is going to be my current forward biased and my current reverse bias. So we get a chart, or we get a graph that looks kind of like this. Now, where do I get this chart? You can look at this chart at any specification for any diode that you want. Trust me, it is there. Now, what can we read by this? What we read by this is this section up here is our forward bias, which means current is going to travel after a certain voltage, and the current is going to go up exponentially. Usually, this point right here is 0.7 volts. This is for a silicon diode, which is kind of standard. I'm going to go with 0.7. So that means it takes 0.7 volts to actually turn on that diode. And once that diode is turned on, current then can flow. And as you can see, the current rises exponentially. Now, in the case where we reverse the voltage and current tries to flow the opposite direction, we get kind of the same thing where the voltage is reversed and then all of a sudden it starts conducting. This tends to be a bad thing. This is where we could damage our diode because we're forcing a current through it the wrong direction. Now, depending on what value this is right here is dependent upon whatever diode that you pick. It can be more or less. It's not necessarily 0.7. But this is how it protects it. So in this section from like here to here, we're protecting that diode against anything that's trying to flow through it. In other words, the diode is off. But if that current or that voltage gets too high, then this breaks down. This is called the breakdown point, and it starts conducting the opposite direction, which is not what we want. These charts are found in any specification. You can look those up and see what those values are for any given specification. There are different types of diodes. I'm not going to get into all of them. This is a standard diode here. There's what's called a zener, which we're not going to get into in this lesson, but kind of looks like that. That's called a zener. And of course, you've seen the LED. These are probably three of the most common ones that we are going to work with, at least in these lessons. Okay, how do you identify these? You can't see it in this picture here, but usually there's numbers on here. They're visible to see. It's not color coded like a resistor, and these are about the same size as a resistor, but they actually print the number on here, and then you can look up that specification. And again, that specification gives you any value, or I mean all of the information about that particular diode. Now, what if we want to test a diode? What if we want to see if a diode is good? So this is one thing that we can do. If we take a diode, and let's take our meter, and we have one probe here and one probe here, and this is our plus and this is our minus. Again, this is our plus and minus. This is our anode and cathode. If we hook this up just to the diode, no circuit in there, we should get a measurement. We should get a value here. That value can be 0.5, it could be 0.7, it could be, depending on the type of diode, it could be pretty much anything. And that's what we would expect. Now, this is how we tell if the diode is good. We can reverse these and now put negative over here and positive over here. If we do that, we should get a 0, usually a 0L. in your meter, which means you're out of limits. That is what we would expect. If we reverse it and we get a number here, that diode is bad, because that means it's conducting both directions. And if it's conducting both directions, we know it's only supposed to go one direction. Therefore, it's a bad diode. All right? So that's how we test. Now, let's go look at an example. So, I have just a real simple circuit here. I got a 100 ohm resistor, which you're already familiar with, the 9-volt battery, and this diode. Now, first of all, we want to look and say, well, all right, well, this is positive here, and this is negative here, and this is the positive side of my diode, and this is the negative side of my diode. So just looking at the diagram, I can tell that my current flow, in conventionally thinking, is going to flow this way, and that's a good thing. I'm going to have current flow. The question is, how much current am I going to have? Now, we know through Ohm's law that we can just use V equals IR, or it's really, for this one, I equals V divided by R if I manipulate that equation. And I have my battery and I have my resistor. But you cannot discount this diode. This diode plays a factor in the current because, as we talked about here, this diode turns on at 0.7 volts. That means there is a 0.7 volt drop across this resistor. Across this diode, which means we're really not putting 9 volts in this 100 ohm resistor. We're putting 9 volts minus 0.7. So really, my voltage drop across this resistor is 8.3 volts. Now, using Kirchhoff's voltage law, we know that the components drops in a circuit should add up to the total. So that's why I took the voltage for the resistor was the total voltage minus the voltage drop of the diode. Okay, so that's my voltage drop. So now if I want to find my my current for this circuit, I'm now going to take this voltage across the resistor, and I'm going to say now 9 volts using Ohm's law divided by 8.3, and 9 divided by 8 point, I'm sorry, I totally messed that up. It's not 9. Let's try that again. 8.3 divided by 100. My voltage drop across the resistor is 8.3. My resistor value is 100. Sorry about that. And that's going to give me a value of 0.083 amps, or 83 milliamps. So conventionally, my current, which is traveling conventionally this way, is 8.3 milliamps. All right, so there's just a real quick example, and we could get power on each one of these components too, but we're not going to get into that yet. One more example that I want to do. If we set these two things up here, I have a plus and a minus battery here, I have a plus and a minus battery here. This means I have potential. So let's say this is 9 volts. And we'll say that, oh, I don't know, let's say this one is minus 5 volts. Okay? And so we have 9 volts of potential coming out here. And our current flow is going to be this way, of course. And because of that, our potential here is high and over here is low. So conventionally my current's going to travel this way and this circuit will be on. Okay? Now, if we look at this one, I have a minus 5 here and I have a 0 here. Because of that, this potential here is less than this potential here. So therefore, current is conventionally going to go this way, and this one is also going to be on. But what if I make that plus 5 volts? Then I have a potential here that's higher than a potential here. The current flow is going to be this way, but we know it can't flow that way conventionally. So therefore, if that's positive 5, it's off. Okay? All right. So let's recap real quick. Diodes, what do we use them for? We use them to control the direction of current. Just like this water example, it's like a directional valve. It allows water to flow one direction, but not the other. We have forward and reverse biasing. Our forward and reverse biasing can be seen in this chart. This section here is for forward biasing. This section here is for when it's reverse biased. We want to be careful if we reverse our voltage. If our voltage is too high and we reverse bias it, we could damage the component. We also have Zener diodes and LEDs. They work very similar. Zener is a little bit different. We'll get into that in a later lesson. When we want to test a diode, we hook it up conventionally with the anode and the cathode to our meter, and we should get a reading. When we reverse it, the probes, we should get a out of limits. If we don't have an out of limits and we do have a reading, then that diode is bad. In our example, we always have to take into consideration in any circuit the voltage drops of a diode. Those have to be calculated into our equation, especially Ohm's law, as I showed here. And down here we just had an example of conventional flow, depending on what our potential is and what that potential, how that potential is flowing, or that current is flowing. All right, if you have any questions, please leave them in the comments. And please subscribe to Web Education.